Hello class, this is Dr. Viv. In this video we shall do a one-dimensional kinematics problem using calculus. So an object, in this case an UFO, travels in a straight line according to a rule given to us. The velocity as a function of time is alpha times t minus beta t squared, where alpha, beta, and time are all positive. So the first question is a units question. What are the SI units of alpha and beta? Then suppose we know that the initial position is 0, what would be the acceleration and position as a function of time? Now, assuming that the UFO stops, what is the acceleration when it's not moving? And finally, draw the graphs for alpha equals 2 and beta equals 3. So let's do this problem. It's a standard one-dimensional kinematics problem that you may encounter either in your homework or in portions of your exam. So let's go step by step. I'll do part A first. The units come from the velocity function v of t is alpha t minus beta t squared. Well, velocity is measured in meters per second. That means each of these terms must have units of meters per second. So I can write dimensions of v must be equal to the dimensions of alpha times t, and that tells me that the dimensions of alpha are going to be the dimensions of v divided by the dimensions of t. V is measured in meters per second and t is measured in seconds, so that's going to be meters per second squared. So alpha is just an acceleration. The other equation I can write is v is also, the units of v are also equal to the units of beta t squared. Well, this gives me beta equals the units of v upon the units of t squared. So that is meters per second over second squared, which gives me meters per second cubed. So those are the units of alpha and beta. The second question, it's easier to find the acceleration first, so we'll do that. Acceleration is the rate of change of velocity, so it's dv by dt, and that's just alpha minus the derivative of t squared is 2t, so it's 2 beta t. So that's the acceleration function. For future reference, let me write it down for the specific value of alpha and beta that we have in part D, so we can plot it easily. So I'll put a different color for that. So that's going to be 2 minus 2 times 3, 6t. So it's not constant acceleration, therefore we can't use any of our constant acceleration kinematic formulas. That's why we have to use calculus. The way we find the position as a function of time, it's the integral of velocity. So that's going to be the integral of alpha t minus beta t squared dt. Now, I just want to remind you of a formula that you may have learned in basic calculus. And that is the integral of t to the power n dt is t to the power n plus 1 divided by n plus 1 if n is not equal to negative 1. If n is equal to negative 1, you cannot use this formula because the denominator goes to 0. And it's equal to the natural log of the absolute value of t if n is equal to negative 1. So this is a standard result from basic calculus. Let's use that. So in this case, n is equal to 1, so I'm going to get t squared over 2, and here I'm going to get t cubed over 3. So x as a function of time is going to be 1/2 at squared minus 1/3 alpha t squared beta t cubed plus some constant c. To determine the constant, we need what's known as the initial condition, which is given to us actually. The initial condition is that at t equal to 0, x is equal to 0. So let's use that. X of 0, which is 0, is equal to, when you put 0, that's 0, that's 0, so that gives me c is 0. So finally, we can write x as a function of time as 1/2 alpha t squared minus 1/3 beta t cubed. I'll confess that I chose the values of alpha and beta to make plotting easy. So this is just alpha is 2, so that's just t squared, and beta is 3, so that's just going to be 3 squared minus t cubed. Possibly the easiest thing to plot. We'll look at the plot soon. Now the next question is to find out the direction of the acceleration when the UFO is not moving. To answer that question, we need to first figure out when the UFO is not moving. Well, not moving means velocity is 0. So let's set the velocity expression equal to 0. I'm going to get alpha t minus beta t squared is equal to 0, which I can factor out a t and write this as alpha minus beta t times t equal to 0. So there are two solutions. The first solution is t equal to 0, and the second solution is t equals alpha by beta. All right. Now let us, once you know the, just for fun, let's also find the locations of x, even though it's not asked. What is x of 0? When you put 0 here, I get x of 0 is also 0. And let's also find out what is x of alpha over beta. When you put alpha over beta here, I'm going to get 1/2 alpha squared over beta squared minus 1/3 beta alpha cubed over beta cubed. So I get alpha cubed over beta squared there, so I better get the same thing here, and I do. So I get 1/2 1/2 alpha cubed over beta squared minus 1/3. So half minus 1/3 is, I guess, 1/6. It's not important, but I just felt like doing it, so I did it. While drawing the graphs, it might be useful, perhaps. The acceleration is what's really important, so let's figure out the acceleration at time 0. The acceleration expression is alpha minus 2 beta t. When you put t equal to 0, I just get alpha. Now, according to the conditions of the problem, alpha, beta, and time are all positive, so it means that this is positive. The conclusion we have is that the direction of the acceleration when the UFO is not moving at time t equal to 0 is it's more positive. Okay, and then the acceleration at time alpha upon beta is going to be, let's put alpha over beta here. So I'm going to get alpha minus 2 times beta times alpha over beta. So that's basically alpha minus 2 alpha, which is negative alpha. And since alpha is positive, this is negative. So that's the answer to this question. At the later time, the UFO will accelerate in a negative direction. So those answers all the questions. And now for the fun part, which is drawing the graph. This is always my favorite part. I enjoy drawing pictures. So there's no particular order in which you need to do this. So let's proceed by simply, at least I would like to draw the graphs one below the other. So let's see if I have enough space for that. Let's try to draw the velocity and acceleration graphs one below the other. I think that might be useful to do. The velocity and the position graphs, I meant. And the acceleration graph I'll draw here. That's not terrifically interesting. The acceleration is just a straight line. Now the straight line I wish to draw is 2 minus 6t. So let me get the acceleration out of the picture by drawing its picture. So 2 minus 6t at t equal to 0, that's going to be 2 units. 2 meters per second squared if you want to put SI units into that. And then at t equal to alpha over, let's see, at t equal to 2 over 6, the acceleration is 0. So at t equals 1/3, the acceleration is actually 0. And then after that, it keeps going down. So this is an interesting graph. What does the velocity graph look like? The velocity graph is, where is it? It's this one here. So it's, so if I want to draw this velocity graph, it's going to be 2 times t minus 3 times t squared. So that's actually a parabola. You can graph that. So I'm going to get something like this. It's upward parabola which intersects the t-axis at t equal to 0, and the other value is when t equal to alpha by beta, because that's the second value where the speed is 0, and alpha by beta is 2/3, so t equals 2/3 is this value, and at those two values the velocity is equal to 0. Now what's interesting is that in the middle value is 1/3, because 1/3 is exactly halfway between 0 and 2/3. Well, 1/3 is where the acceleration is 0. But acceleration is the slope of the graph of velocity versus time. So this tells us that the acceleration is 0 precisely when the slope of the velocity versus time graph is 0. So you can see all these interesting relationships through these graphs. Lastly, let's plot the position versus time. That is just here, t squared minus t cubed. The fact that it's t squared means that at the origin you're going to have a point of inflection. So, remembering your calculus things, the graph is going to look like this. And then we're not concerned about anything less than 0, so we don't worry about that part. And then it's going to go up like this, and then it's going to come down at some place like 1, obviously, because at 1 you get 1 minus 1, which is 0. So this graph is going to look like that. And the velocity is 0. So if I had drawn this a little better, I would have stretched this out so that 2/3 and 2/3 lie below each other, but I won't try to be an artist here. This is 2/3. I know it must be 2/3 because there are only two places where the tangent is horizontal. One is at 0, where the velocity is 0, and one is at 2/3, where the velocity is also 0. So this would be the velocity equal to 0. Lastly, there's one more thing I wanted to point out, and that is the acceleration is positive here because that's the slope, and indeed it is positive. It's 2, value is 2 there, and the acceleration is 0 there, and then at 2/3 the acceleration is going to be negative. I have not drawn the acceleration graph that far, but at 2/3 you can imagine this thing is going to go down and the acceleration is going to be -2.